let's start. Oh, before I start, so this is the last lecture. All the homework are due, I believe, on the 4th, right? That's what I said. Yeah, just make sure you put them in because that's really my last time to make sure we can get them read if I graded and I can submit the grades. All right. Review of the previous lecture. If there are any questions, please ask. So last time we started our discussion of large N perturbation theory. We said that quantum field theory, oops, what am I doing? Yeah. We said that quantum field theory simplifies at large N. I just said intuitively, even though we won't have time to go through large N global symmetry, but intuitively the idea is that if the number of degrees of freedom is proportional to N, like Gross de Novo model or CPN -1 model, these models end up being solvable. They become so simple that they're solvable. But the number of degrees of freedom is like N squared, and Yang-Mills, they're simplified but not solvable. We'll see that they become Gaussian theories. So Gaussian sounds like Gaussian means that all the connected correlators go away. All the connected higher point functions go away. But the 2-point function is a genuinely interacting 2-point function, right? Do you remember? So we had the Callan-Lemon representation of the 2-point function of an interacting theory, right? That said that it's basically an integral over the 2-point function of Curie theory, but then there is spectral density, rho of M squared. So it's an integrated version of that, right? Turns out that for these large N theories that we're discussing, that spectral density has support on infinite points. So it's like a series of infinite massive set of states. These are the single trace operators. Their masses are coming from the spectrum of dilatation. Those we don't know how to find. So when we say the theory simplifies but is not solvable, it means that we don't know how to calculate those masses. Because if we had the 2 function, Wick's theorem gives you everything, right? The theory would have been solvable if we had the 2-point function, but the knowledge of 2-point function is hidden and is equivalent to finding those masses. We're going to say today that those masses are the masses associated to single trace operators. We're also going to say today that those single trace operators are glue balls. So these are the energies. The binding energy of glue balls is what we do not know. The theory would be solved if we're given the list of binding energies for these glue balls, right? All right, we're going to go through. Good. We started a discussion of the last lecture with hydrogen atom at large N. This was just a principle for just like a little calculation to see what was this large N all about. We said that let's say Schrodinger equation and try to solve it without solving it. We first write in dimensionless form, M alpha squared. This energy scale is the energy scale that sets the excitations is off just by a factor of 2. In the large D approximation, what we did, I just want to emphasize this part, I'm not going to repeat it, is similar to DIMREG, we keep the form of the interaction 1 over R, but we just treat the dimension as a large parameter. So if you wish, this is as if like 3 is a large parameter, right? So we're going to treat D as a large parameter or N as a large parameter. We found that this was the what am I doing? We found that the energy of ground state in 1 over N expansion like this, when you put N equals 3-dimensional space, this is the number you find, whereas the energy of the ground state is the true value is this. So you're off by a factor of what is it, 4 over 9 or something. So it's almost half. Then we start talking about large N Yang-Mills because usually any presentation of large N theory starts with large N global symmetry because it's easier. We had seen some aspects of that when we calculate the beta function for the ON model, and we saw how it led to these Wilson-Fisher type fixed points. But we just focus, we started because of, we don't have much time, we focus on large N Yang mills. Pure Yang mills is what we start with. Here's the action. The beta function takes this form, N enters through the C2 of G. And then there is a Landau pole because this is asymptotic with 3. There is a Landau pole at scale lambda that decides the lambda QCD. This Landau pole at one loop is basically given this way. From which we concluded that if you're sending N to infinity, keeping G finite, we run into the trouble that lambda QCD, which is the scale IR scale with this, where the theory is strongly interacting, becomes the same as lambda UV. So it just means that the theory is strongly coupled. There is no regime where the theory is like weakly coupled. So that's not what we want to do. Well, so that's because what we want to do is we want to work with in a setup where you send N to infinity, G squared is going to 0, keeping G squared N, so-called 't Hooft coupling, fixed. Now this way, lambda QCD is will remain the same. You could be working, if you work at energy scales larger than lambda QCD, the theory is perturbative. The effective perturbative parameter is lambda 't Hooft coupling. If you're working on lower scale below lambda QCD, the theory is strongly coupled and lambda QCD is large, right? It's becoming large, right? Well, sorry, lambda QCD. The theory is strongly coupled. All right, is that good? So that's the origin of 't Hooft coupling. This is the argument that 't Hooft had for introducing his parameter. So we said that we usually, well, if it's a theory that's SUN, we'll have to represent it like the gauge field becomes a Lie algebra valued field. And then we said when N is large, there is no distinction between UN and SUN. That is pretty obvious from the form of the 2-point function. When N is large, basically independent matrix elements act as if they're different matrix elements act as if they are independent, right? So you could just view A mu IJ, some matrix basis to be your basis fundamental fields, and that suggests a simplified double line notation, right? So I and J is like fundamental, anti-fundamental indices. Because of the normalization that we had, the propagator, this is going to be important when we make the comparison with QCD today, later on. The propagator for the gauge boson is lambda over N. All right, just keep these parameters in mind. With this way of normalizing things, which had 1 over G squared outside of the action, said differently, lambda N over lambda outside, right? With this way of parameterizing things, the advantage is that in the gauge theory, when you expand the 3-point and 4-point vertices, they're both proportional to N over lambda. So basically, you're dealing with lambda over N for every factor of propagator, and for every vertex, whether it's 3-point or 4-point, is N over lambda. Right, so the inverse of that. So it simplifies the counting. You don't need to distinguish between 3-point, 4-point. So in the double index notation, this is the form of it. So a general diagram will have a number of propagator. Each propagator is going to be lambda over N. A bunch of vertices. Every vertex is N over lambda, hence the minus. And then there will be index contractions because it's effectively N squared number of degrees of freedom, N for the N and N bar, fundamental and anti-fundamental. You will just have to take N to a pair of number of index contractions, right? So from that, we saw that if we look at bubble diagrams, a bubble diagram that looks like this is lambda N squared. A bubble diagram like this is lambda squared N squared. So as N goes to infinity, these two guys survive. This is, or these two guys are large. This is if 't Hooft coupling was small, this is lower in 't Hooft coupling than this one. But we're not going to take 't Hooft coupling to be small. We want to be in some arbitrary 't Hooft coupling, but large N. But then the non-planar diagram like this, because of the index contractions, it will be 1 over N squared suppressed, which means that as we take N to infinity, it will just drop out. This planar, non-planar, we explained it as a diagram is planar if you could just put it on the surface of a sphere as opposed to higher topology things. And the diagram would go like lambda over N to the power of E minus V, N to the power of F. F is the number of faces. So it means that if we write everything, it will look like N to the power of chi. Chi is the Euler character of a closed Riemann surface, right? So it's just 2 minus 2g. For sphere, it is 2, right? For torus, 0. G is the number of holes. Lambda, the power of lambda is not topological, so that's why we're not organizing anything in some perturbation theory in small lambda or something. We're just in large N. This is actually the origin of the connection between large N limit and string theory, but that won't matter for us. Any questions about this? Yeah.
Why is two-dimensional sphere and not, for example, an infinite plane for the planar diagrams?
Call it infinite plane. It's just same thing.
Does it not like are the diagrams like wrap around the sphere? Is that why you're referring to it as a sphere? That's
No,
that's right.
no. It's just a point. That's conformal compactification thereof. Yeah. We're talking about bubble diagrams, right? Do you know why I'm talking about bubble diagrams? Because I want to calculate phi energy, log of z. And then I take derivatives. I get, yeah, okay. So you remember that. So large N limit is classical. The gauge invariant observables of Yang-Mills should be Color singlet. There are two types of such things. There are the non-local observables of gauge theory. These are Wilson loops. We will not be concerned with these guys for now. They play an important role in the phase diagram of the theory. When you have finite temperature, the time-like Wilson loop will be an order parameter for phase transition, blah, blah, blah. But we're not discussing any of that. What we're focused on is local observables that must be gauge invariant. And such observables will have to be basically traced. So they have to be trace of F mu nu squared. Well, trace of F mu, well, I'm sorry. This is, what did I write here? Yeah, actually, that's fine. Yeah, let me not say this. The simplest example that we have is trace of F mu nu squared. But when I say squared, I mean just like put whatever in the Lorentz index contractions, Lorentz indices you want. In general, single trace operators will be operators of this form. Notice that, so these are composite operators. They're like phi squared at point X, right? We could define them using point splitting or all the techniques that we had before, right? Now, if the theory was free, what would be the, so and if the theory were free, the conformal dimension of, the scaling dimension of F is, if the theory is free, right, it's gauge invariant. It's scale invariant. If lambda is small, right? What is the scaling dimension of F? Yeah, it's 2. What would be the scaling dimension of F squared? 4. So they would just, as a free theory, they just multiply, they add up. Now, when there are lambda corrections, there will be lambda corrections to this, right? That is precisely what, so we don't know a priori the scaling dimension of trace of F squared. That's if we knew that, finding the scaling dimension of f squared is precisely this problem mass that I said. It's the mass of this excitation. Once you put it on a sphere, it's the mass of the excitation. Well, I haven't explained any of that stuff anyway. There are the multi-trace operators that are like this. But multi-trace operators, we need to keep the, well, okay, no, sorry, that's fine. What we're gonna do is we're gonna calculate the correlation function of single trace operators. So here's what your favorite single trace operator. You put a source next to it, and the goal is to actually evaluate the correlators connect the correlators of this single trace operator. The way you calculate that is that you calculate the partition function with this action. You take the log of it and you take derivative with respect to j. This n to the power of p is just a proper normalization. Good. So the action in front of it, this is very, very crucial. In this normalization that's relevant for large n, there is an explicit n sitting outside of the action. Free energy goes like n squared. This is what I meant when I said in gauge theories, the number of degrees of freedom go like n squared. The theory is simplifies, but it's not solvable. This is to be compared to the global case where I said the number of degrees of freedom scales like n. I meant free energy scales like that. So the connected part of the correlator is scaled like n to the power of 2 minus p. So that's Gaussian. It's a free Gaussian thing. Actually, I think, let me explain on the board a little bit more. That means that the 1-point function is what is the 1-point function? So the free energy is just the expectation value of 1. It's order n squared, right? P is equals 0. When we look at the 1-point function, that's order n. In the strict n going to infinity limit, it blows up. So you can't work with single trace operators literally. What you can do is that let's look at the 2-point function. The 2-point function, GG is plus GG connected, right? So the 2-point function, each of these guys is order n. This is order n, n squared. This is order 1, right? So to make things clean and well defined in the large n going to infinity limit, what you do is you take the single trace operators, you subtract from it the 1-point functions, right? You remove the 1-point function. Now it's an operator with 0 expectation value. It has fluctuations. Its 2-point function is the connected one. It's order 1. It's good. Its higher point fluctuations vanish as n goes to infinity because of the power of 2 minus p. That is what is Gaussian, right? So let me repeat. You take the single trace operator. The 1-point function of that is order n. So if you take the strict n going to infinity, the limit blows up. It's nonsensical. You have to remove the 1-point function. You can always shift the value of an operator. So the thing, after you take the n going to infinity limit, the thing that you're considering is the 1-point removed single trace operators. You take the limit of those guys survive the limit. Acting on the vacuum, they create unit order what things that are normalizable. Right? Otherwise, if you work with these guys acting on the vacuum, they create a state that's not normalizable. This is the norm of the state, right? So that's what we work. Good. The fluctuations are suppressed. And that is what's Gaussian. I said this, oh, the single trace operators, we're gonna call them blue balls. Now, yeah, okay. Any questions? So I just reviewed what we discussed last time. All right. So let's focus on the connected two-point function. This is a gauge theory. So the diagrams we're looking at, remember when we had non-abelian gauge theory, here were the diagrams we looked at. So here are the one loop diagrams. There was the 3-point, 4-point, three-point vertex, one loop with two insertion, 3-point vertex, this guy, and then there was this was the ghost part to just make sure everything is good. There's two loop, all sorts of diagrams, and hard loops are crazy. In the large n limit, when we talk about the 2-point connected correlator, we mean that every diagram here is allowed as long as it's planar. We're just gonna drop, we're gonna go to arbitrary loop. We're gonna sum arbitrary loop diagrams, but only the planar ones. Right? And of course, connected diagrams. So one, yeah. So these look like, if you in the notation that we're using, these look like two of these sources and sum over all planar graphs. This is one particular contribution, is this double line notation. These guys need to be resummed to give you the connected two-point function. This is the part that we do not know how to do. Right? This is the part that we do not know how to do. But if I'm going to say in a second, the result of this calculation is a set of an infinite set of numbers. If you give me those infinite set of numbers, I know everything about the theory. Because the theory is Gaussian. G8, every time you have these Gaussian modes, you could always diagonalize them. And then you could view them as like creation and annihilation operators. It's just it's the same algebra. A generic, so these create single trace operators. A generic two-point function, which is the sum of all these guys, from the Callan limit, will have a spectral density. If you remember, Callan limit was like this. So we take the two-point function, write it this way, and these ANs are just the coefficients, the single particle with mass Mn. No, like anyway, you know what I mean. Callan limit, we did this, right? In principle, there would be a continuous spectrum. In these large N theories, you could argue that there's a discrete but infinite set of these modes, and they correspond to the masses that we associate to the single trace, these glue balls. They're the masses of these glue balls. So there is, of course, I'm spending half a lecture on this. You can read so much on this, you could do so many calculations that are important. I just want to give you a hint as how the structure of this goes. You could also argue that these cannot be a finite number of them. There has to be an infinite number of them. The consistency of the theory requires an infinite number of such massive modes. So at large N, the theory looks like an infinite set of decoupled massive free modes, harmonic oscillators. That has a name. It's called generalized free fields. Such a theory is called generalized free fields. Every time you hear generalized free fields, it means a collection of decoupled massive free fields.
Why generalized?
Because the massive free field is just a single mass.
One, I mean, like, if we have a collection on the outside, why not just call them free? Why not why general? Presume there's a reason.
Yeah. So take the two-point function. Callan limit representation. What does it say? It says the following. So take the two-point function of massive free fields. Right? What is it? It's k minus k. Right? It's 1 over k squared minus m squared or whatever. Right? Take Callan limit says Same thing in an interacting theory. So this was free. In an interacting theory is an integral of d rho m squared, some function, yeah, well, actually, no. 1 over k squared over m squared. Right? So free field corresponds to what choice of spectral density? Delta function, right? Yeah, it's a delta function. M squared minus the actual physical. Right? This is a free theory. And then all the higher point function in the free theory can satisfy Wick's theorem. In the interacting theory, they're whatever they are. Now imagine a theory that satisfies Wick's theorem, but the 2-point function is not just one delta function, it's a sum of these guys. It's a general spectral density. It's called generalized free fields. That's what we're finding here. We're finding an interacting theory where the 2-point function is not a Dirac delta, it's an infinite set of these masses, right? It's an infinite set of such masses. However, all the hard point functions are satisfied Wick's theorem. That's why it's called generalized free fields. Because of the sum. It's sorry, one thing. It's conceptually very important to realize, I can say it a little bit later maybe. Generalized free fields have non-locality in them. I can tell you more about it if you want.
Wait, why did you guys turn into a sum instead of an integral?
Oh, it's in this particular case is how it turns out. They have to do with the fact that the counting of the single trace these guys correspond to single trace operators. And the number of them you can count, trace of phi squared, trace of phi cubed, phi 4, phi 5. You have to make them orthogonal, right? But you could do that as well.
Yeah, just to clarify, for the infinite number of modes, the sum converges because the higher modes disappear by ways through.
Sorry.
I'm saying like in the limit n tends to infinity, like does the sum
N
converge?
is so sorry. Which N? Capital N?
Yeah, capital N. Speaking of
Yes.
capital N goes to infinity.
Yes.
So it converges because of the higher modes get cancelled into Wick's theorem. What is the reason for the convergence of the sum?
Sorry, convergence of which sum?
I mean, how does it look in the limit in n goes to infinity? This is the expression.
This is the expression that, sorry, capital N has gone to infinity,
Yes.
and whatever I've written on this board, the whole is literally capital N to infinity limit. In the N equal infinity.
Yes, I understand that. Now I'm saying that in that limit, what about the small n? Because we argued that there can be infinite number of mass
No,
modes.
it's not that like they can be. There is an infinite number.
So what about this summation now in small n? Does it converge to
In which theory?
in the large n goes to infinity through?
It's always an infinite number of them.
Okay, that's what I was.
The consistency of the large N limit requires that there is the sum is an infinite number of modes. I can tell you more about it. You can read on David Tong's notes as well. This comes from the behavior of you can argue for this. It comes from the behavior, the high energy behavior of 2 points. Yeah.
So what happens when you start adding corrections for non-infinite n? Does the theory immediately go haywire or is it perturbatively nice?
There is a systematic 1 over n perturbation theory. And we had to talk about the over n square perturbation theory by Anya Sabisi a couple of weeks ago. She talked about these multi-trace operators, and it was before all of this stuff. I don't know how much of you guys understood from that talk, but there's a systematic 1 over n squared perturbation theory. It's important to say that this is all nice when you build, this 't Hooft coupling was designed precisely, this 't Hooft limit designed so that there's a nice 1 over n squared perturbation. To mathematically make this rigorous, it's a different framework as small coupling perturbation theory. So this framework goes with the name of deformation quantization. It's like there's a mathematically different construction. All right. Any other questions? All right, to summarize, here I'm just gonna this is the only slide that I have that makes a reference to UN or like global symmetry. The story in the global symmetry is not very different. You have an action, an ON model or UN model like this if it's complex fields. And here you have a gauge invariant SUN model or UN. I said there's no distinction between the two as in the strict n going to infinity. The distinction, the important thing is that the singlet operators are, sorry, all observables are singlet in the gauge theory because of gauge invariance. So the operator that's not singlet, something that's not singlet transforming some other representation is just nonsensical in the gauge invariant theory. And the global symmetry, these are excitations, but they end up being massive. So this theory has more degrees of freedom, right? But we often still look at singlet sector. So the singlet, the singlet single trace operators. So singlet sector will have single trace operators or multi-trace operators, right? Single trace operators, examples are like this or like this. Multi-trace is like this. So I said this before, if O is a single trace operator, the 1 point function of it is one order, the 0 point function is order n squared. Now I'm talking about gauge theory. That just means that the free energy is order n squared. The 1 point function is order n. I said that, you subtract it, so you get something sensible. Now the 2 point function connected parts is order 1. That's good and nice. That just means that the 2 point function, the full 2 point function of the 1 point subtracted operators is actually finite. So there's a Hilbert space you can construct. If you know about the genus construction, that's the Hilbert space you construct. And the hard functions are 1 over n.
Yeah. So why does global symmetry?
Oh, I have not explained that. Just have to read about it. No, it has more degrees of freedom. It has n is n as opposed to n squared. It has to do with the okay, go ahead.
So the states that are allowed in global.
My bad. Let me clarify. It's not about, it's about the group. The ON model, right? The fields are transforming, they were in the fundamental, right? So the number of degrees of freedom is n. It's a vector model. So the distinction is between vector models as opposed to like adjoint matrix models. That's the distinction. N squared versus n. Sorry, I should. Yeah. I caused confusion by my comment. Sorry about that. So a bunch of comments, and then we'll move on to large N QCD. In the large N limit, these 1 point subtracted operators acting on the vacuum, they create a glue ball. Even though I'm not writing the 1 point subtracted, but that's what it is, right? What happens if you act with this twice? You create 2 glue balls. So it's like a creation operator, right? We can diagonalize these guys. Actually, we have to diagonalize this so that we have this creation operator picture. So that's what we usually do. Then the correlation function between the multi-trace operators and the single trace operators is 1 over n suppressed. That just means that the single trace operators just close on themselves. They don't talk to multi-trace operators in the strict n going to infinity limit. So 1 over n perturbations theory is complex because of mixing between the single trace and multi-trace. This is what Agnieszka's talk was all about. She was to go around all of this was what she was doing was that she was taking an example for super Yang-Mills. She was looking at particular single trace operators that had half BPS symmetry. That means that they had a lot of symmetry. That meant they could not mix with arbitrarily with multi-trace operators. So there was a specific theory. There was a lot of symmetry, and some of the single trace operators had so much symmetry that this mixing was limited. So she had some analytic handle. And that was the start of her talk. Right? The fluctuations of glue balls are suppressed. We said that, they're Gaussian. Right? All right, good. Question? All right, large NQCD. Large NQCD is basically the theory that we just discussed. You add to it fermions, right? For example, let's say you add one flavor of fermions, but you can probably, as you remember in large N examples we were discussing, you can add more than one flavor. You can add NF flavors, right? And then you could arrange actually for funkier analogs of toothed lymph. But here we're just adding one flavor because you don't want to mess with anything else, right? Now here's your fermion propagator. Your fermion propagator is order lambda over n. What was the gluon propagator? Lambda over n. So they are at the same order, which is good. That's good, right? Now the gluon interacting with the fermion has this diagram in the double line notation. This comes with factor n. That's an interesting twist. So this vertex comes with a factor n. And then, for example, okay, that's all that there is. These are the two new diagrams you have to consider, right? Now, a diagram like this looks like this. So this is lambda over n to the power of cube. Why? There are three propagators. One fermion propagator, another fermion propagator, and this is a gauge field propagator. So there are three of them. Then n to the power of 2. This is because there are two gluon fermion vertices. And then n to the power of 2 because the number of loop index. One loop index, two loop index. You add them up, this is lambda cube n. Good. Previously, we had everything was organized as n squared, right? We were just getting n squares all the time. Here, we're finding like n powers of n as well. So I'm going to say that in the comment that I a little bit. Let's take another diagram. So this diagram is like this. It translates to this. So if you do the counting here, you get lambda 6, 1 over n. So this is lambda square, sorry, n squared suppressed compared to this diagram, which is reasonable. So a general diagram, I won't have the time to go through it in detail because I want to summarize the whole course, but a general diagram will look like this. N to a power of number of faces plus the number of vertices minus the number of edges. That's the dependence on n, and the lambda to the power of e minus v. As usual, this is not topological. This is chi topological, and this is the Euler character, but it's no longer for 2D Riemann surfaces that are compact. We allow for boundaries. What is a boundary? Well, these are boundaries, right? There's one boundary. So this is the Euler character for 2D surfaces with boundaries. In the example analogy with string theory, these becomes the open string. So there are boundary conditions that it doesn't matter. There's closed strings versus open. So gluons become closed strings. These guys become open strings. All right. So now that we include fermions, you're going to end up with mesons and baryons. I'm just going to comment on mesons. Baryons are a little bit more, I try to include them, but it's a long, it's a can of worms. If I open it, it goes on and on. So the mesons are the only ones that I'm going to comment on. So mesons are bilinears on side, right? Good. There are side bar side, but FM in the middle, in principle, right? Square root n. So there are a lot of these mesons. You could show that the connected piece of these correlators are n to the power of 1 minus p over 2. Yeah.
What is M, the power? And so-
Some power, any power. So there's an index M here.
So for any M, it's n to the power one minus p, right?
So just let me make the. Yes. The comparison was precisely like this. Before, what we had was trace of f to the power of m. This was some g. And I said, you know. This guy was 2 minus. K. Yeah, 2 minus K. Connected. Same rules here. But what happens is that you make them orthogonal, right? So that you don't need to mix different ones. Right, that's what we did. So here is n to the power of 1 minus p over 2. Meaning what? What is the 0 point function? What's the meaning of the 0 point function? It's order n. It's the contribution of these fermions to the free energy. We add the term to Lagrange, right? It's n. So it's suppressed compared to n squared of the gauge boson. So the free energy is dominated by glue balls. Then you have the 1 point function, which is order square root of n, precisely. You subtract it, you get an operator whose fluctuations are the connected correlator of this guy, and they're ordered 1. And all the hard point functions vanish as before. So as this guy creates excitation that are normalized, blah, blah, blah. So this excitation is called the meson.
Why is the square root of n as a coefficient?
It's the right normalization. If you put something else, then your powers don't, you can't arrange them. Well, you cannot make sure, you cannot arrange for this setup that you end up with a connected 2 point functions. That's order 1. Higher point functions that are suppressed. And these guys decoupling from the glue balls. Right, that's a correct. So there's something this goes into the large n limit, right? You find these excitations, you can organize your excitations this way. Of course, you can put some other power there, but then they don't have a good n going to infinity limit.
So it's basically you put some power test from what powers of the power, what powers of n were, and you sum the counter n to power half.
Correct.
The half power.
Correct. This is the same thing as putting in, well, okay, never mind. I'm not gonna over explain. Okay, good. Now, what happens is that these mesons are free, I'm sorry, but also they don't couple to the glue balls. You end up with free mesons and free glue balls. They don't talk because you can show that their correlators is like this, which means that the 2 point function square root n suppressed. So they don't talk to each other. The baryons of this theory are, I'm just gonna say one comment. They're like psi to the power of, well, okay, no, I'm not. I won't comment. Never mind. Any questions about mesons? Because I want to summarize it.
Those two, what do you call it? Those are connected objects, right? Or
Yes, connected. Everything connected. Everything is connected. These are derivatives with respect to log of. See. So similarly, you can take the 2 point function and look at the Fourier transform it, and the Callan-Lehmann representation will give you meson masses. So they're in the spectrum. They're blue balls, they're mesons, and all of that. Good. We do not know, we cannot show whether the theory confines or not. Right? Because we cannot compute these guys. We just showed that there is some sort of Gaussian limit. However, if it does confine, then the single trace operators are relevant. All right, any questions? Yeah.
So do these computations actually help with like n equals 3 QCDs, or is this just basic theory building?
Do they help?
Like, can you do these kinds of computations to actually do QCD calculations, or is that sort of too far removed from this?
You're saying that can people manage to make, is the state of the art of, sorry, what is the other approach that we have for our QCD? It's lattice.
Yeah.
Lattice beats everything. Right? 1/n perturbation theory for n equals 3 is not comparable to lattice methods, because lattice methods are incredibly good. But I'm no expert. So someone who has spent his life or her life on the field, they might tell you, oh, there is this particular calculation with 1/n. That's something right. Yep. I can tell you for sure it's not the dominant approach.
Yeah. So this is like helpful for other theory building, not necessarily.
And other reasons that I will say. These are quantum gravitational theories. All of these are theories of quantum gravity. All right. Any other questions before I start summarizing quantum field theory 1 and 2, actually? I'll summarize them all. All right. So in this course, we're predominantly talked about the Lagrangian approach to quantum field theory. I just want to say in words that we quickly hinted at operator product expansion of OP approach to quantum field theory. Very briefly talked about this. And then there is another approach that I want to highlight, is the algebraic approach. They're all related, okay? They haven't had nearly as much success as these approaches. Actually, OP, you have to put it in a different category, but anyway. The principles that I started quantum field theory with in QFT1, I'm going to repeat them, and now they should click. Locality, symmetry, and renormalization. And as we go through them, I'll explain all sorts of extra things that we discussed about them. So renormalizability or renormalization, I said separation of scales. What does that mean? It means that you take your action, you want to write a local Lagrangian. You want to write a local Lagrangian. That's locality. It has to respect your symmetry. So you're confined by writing terms that are Lorentz invariants, for example, if you're a Lorentz invariant theory. Renormalizability tells you start expanding in the number of fields and derivatives. And in principle, if there is a separation of scales, you can stop after a bit. Only the relevant terms matter. Separation of scales means what? It means that the theory will have some degrees of freedom that you don't know about. But those degrees of freedom don't mess with the infrared modes. Those are all irrelevant. That's separation of scales, right? This is a principle that was hard to explain day one. It was very hard to explain this because you had to see these loop diagrams, a renormalization group, how the couplings grow, how nonsensical it is when you write down a Lagrangian to include f to the power of 26, phi to the power of 26 in your action. You could do it, but it sounds absurd. So the justification that you don't write that term in your Lagrangian is renormalizability, separation of scales. Here, I don't mean renormalizability, I say renormalization, right? Separation of scales. In physics, I don't need to know about quantum gravity to build a building. That's what it is, right? We said that, well, the principle is locality, so local functionals of space-time, but then we immediately said gauge theories are these theories that have non-local observables. These were Wilson loops, and we insisted on local description, hence the gauge invariance, all this redundancies of description, blah, blah, blah. Remember that stuff. We said the symmetries of the action gave us conserved charges, Poincare group. These were represented as unitaries in the Hilbert space. We discussed the definition of the particle as E-reps of the group. Then we saw there are theories with larger symmetry groups, right? That played an important role highlighted by renormalization. These were conformal field theories. They had extra generators, D and K mu. Once you have these larger groups, you organize everything in terms of EREFs of the conformal group. They are fundamental building blocks. So the scaling operators become the analog of your single particle states. So conformal field theory, in standard terms, doesn't have particles, right? But still, the building blocks are EREFs. And you remember how we did that? We looked at we looked at the Cartan, right? We took it and the maximal ability subgroup, which was spin, the quantum numbers for it were spin, well, actually, and scale dimension. Yeah, anyway, so that whole story. Something we did not discuss at all was supersymmetry. It's yet another larger group symmetry group. We did not discuss that, but of course it helps. We said that the symmetry is the whole intuition classically, but then sometimes it's anomalous. It doesn't extend to the quantum world. We saw this in many ways. One way that we saw it initially, we encountered it was when we couldn't pick a regulator that preserved the symmetry. But then later on, we said that that has to do with the fact that the action is invariant, but the measure of the path integral is not invariant. And the measure of the path integral, we calculated how it worked. There was a determinant that creeped up, right? So that was the story of anomaly. We said gauge anomaly for theories that had gauge invariance. Gauge anomaly leads to an inconsistency of the theory. So it's essential that we cancel it. In the case of gauge theories, there was related to topology. We commented on this. About renormalization, there was a long discussion of renormalizability, beta functions, running of couplings, all of that. That I'm not going to review here. But the idea to keep in mind is that every quantum field theory comes with a cutoff scale. The cutoff scale, hopefully, is much smaller. Length scale is much smaller than length of interest. That is, and then on top of it, there's renormalizability, which is the perturbation that the cutoff scale are not going to mess with your physics. The vast majority of perturbation on small scale, we're not going to mess with your physics. So you can focus only on the IR relevant degrees of freedom. Right? IR physics includes relevant physics. The word relevant is so smart, right? It's such a good choice. Whoever came up with the word relevant degree of freedom. We discussed perturbative methods. Most of the course, QFT 1 and 2 was about perturbative methods and Feynman diagrams. We did loop expansion. One loop was pretty much all we did. We had one lecture about two loop lambda phi 4. But also, we commonly spent half of this course talking about the QFT2 talking about non-perturbative methods. I want to list them here. Anomalies are non-perturbative. Operator product expansion was an inherently non-perturbative approach. Instantons were non-perturbative. Do you remember why? How does the action of the instanton depend on the coupling? Think about that. It was e to the power of -1 over g squared, and that doesn't admit a perturbation expansion. And they're also tiny. Then the large n is another non-perturbative approach. We just discussed this, 't coupling. So, good. We constructed, after a lot of work, genuinely interacting quantum field theories. A bunch of them that we constructed in this course explicitly was we constructed large n theories that had Wilson-Fisher fixed points in 3 dimensions, for example. These are setups where you start with a trivial theory in the UV, you perturb it by a relevant deformation, and you ensured that the whole flow within the RG stays within the perturbative regime, and you hit a fixed point. We talked about 2-dimensional versions of that and nonlinear signal models, but there was the issue of instability of the fixed points that we found over there. We talked about Yang-Mills as asymptotically free theories. These were fully sensible actually strongly interacting theories in the infrared. The Yang-Mills theory is basically rule, right? Standard-model particle physics. We talked about the way it works is the phenomenon anti-screening. Right? And that anti-screening was made possible thanks to contributions of non-abelian non-abelianness of the algebra, non-abelian gauge theory. I guess sits on top of this beautiful structure, standard model of particle physics. It is a gauge theory with gauge group SU3 colored times SU2 left times U1 hypercharge. We described what the matter content was. We said that SU2 left is kosher because we check Cardan anomaly. We discussed spontaneous symmetry breaking, how it produced masses for all the fermions. We talked about the phenomenology of it. We talked about neutrinos, all of that, right? We briefly mentioned unsolved problems, hierarchy problem, neutrino masses, and beyond standard model particle physics. We also discussed nonlinear sigma models. We use them to build examples of fixed points in two dimensions, near 2 dimensions. But I want to say that I want to highlight how it led to unification, viewing quantum mechanics as a 0 plus 1 dimensional Q of T. That electrons, right? Just switching the role of space, time, and target and internal space. Going with the same philosophy, it naturally lands in the world of string theory. Very, very naturally. Because it's just a 2-dimensional nonlinear sigma model. It's a 2-dimensional quantum field theory where the target space is space-time. All right. So, of course, it's a short course. We don't have time to discuss too much about the whole world of quantum field theory, but I want to say I made some effort. I attempted at hinting at some very important developments, no longer new developments, they're now decades old, of active areas of research in quantum field theory. Besides, like strong coupling, confinement, which remains an open problem, is if you want to make $1 million, that's the quickest way. There are problems that we hinted at. Curved space-time quantum field theory. The issue over here is that everything was built around the symmetry group that was Poincare group. In curved space-time, that's no longer the killing vectors of the metric need not be that. So we don't know what the symmetry group is. It might not even be something nice. How do we go about defining states? The vacuum of quantum field theory, on top of which we built the Hilbert space, was the invariant state, right? Here was the idea, we hinted at the idea of Hadamard state. This is something that looks class level. Looks almost like flat space. There's no Hamiltonian. Why is that in curved space-time?
Can't be separate space and time.
No. FS orientable is fine. Because there might not exist a global time-like killing vector. Right? But all of this is intimately related to the choice of the Hadamard state and operator product expansion. So if you want to read more about this, look up Bob Wald and whatever he has done in the past couple of decades. There's the issue of quantum gravity. We did not talk about gravity, but let me just say one thing. We said in passing, gravity is non-normalizable. So it does not have this nice feature of normalizability we've been talking about. And that's very manifest from the action. That's the action. What's the dimensionality of G? G is the coupling. G Newton is the coupling. So, sorry. Do you know what the dimensionality of R is? Richie scalar. It's 2. Because the metric is dimensionless, it's two derivatives of the metric, that's just two. Is D4, that tells you that G has dimensionality -2. So it's irrelevant. So the theory is non-normalizable. We don't really know how to make peace with it. You might say the elementary particle of this, if you just try to analyze it as quantum field theory, is a spin-2 massless particle. You might say, oh, a spin-2 massless particle might not be fundamental, could be emergent. Right? Maybe there's some sort of a quantum field theory that in the UV doesn't have a spin-2 massless particle. But in the infrared, the theory gets strongly coupled and some massless spin-2 particle comes out. As we saw in the case of phonon, we saw massless scalars appear in the infrared. Why is that not possible? Turns out there's a no-go theorem. It's called Weinberg-Witten no-go theorem. They prove that such a thing is not possible. So gravity cannot be emergent in a trivial way. Now, there's a caveat to their argument. And they argued the way that we would argue. We argued for phonons. You have a quantum field theory in d dimensions. You perform a normalization group. And in the infrared, they showed that there can't exist spin-2 massless mode. The caveat to that is something like this. You can have a quantum field theory. You could do RG flow, and there might be an excitation mode, but that excitation mode is massless, but the flow has spin-2 in some higher dimensional emergent theory. So this is the boundary of some larger dimensional thing. That spin-2 is spin-2 with respect to representation theory of this higher dimensional space-time. That's actually how holography works. Gauge gravity dualities, we also hinted at, well, we didn't hint at it, but these large N gauge theories that we're talking about are precisely those kind of theories. These are theories where these are gauge theories, but happen to be secretly quantum gravitational theory. The role of G Newton, so this has dimension of L Planck squared. So in Planck units, it's just a number. This is 1 over n squared. And the math that you write down. Now, large N gauge theories have another coupling. What is it? 't Hooft coupling. What does 't Hooft coupling correspond to? If you take Einstein's equations, it's second derivative in the metric. What about higher derivative corrections to it? The theory is irrelevant, you might as well include all of them. Just include higher derivative ones. The higher derivative ones come with a coupling suppression. That's called alpha. That's like the higher curvature correction. The higher curvature correction, the size of them are controlled by 't Hooft coupling. In the large 't Hooft coupling, those corrections are suppressed, you get just gravity. This is how gauge gravity dualities work.
How do you define the high derivatives in case of the Ricci theorem? How does that change?
So square root minus G R add R mu nu R mu nu add higher derivative terms. So like R mu nu alpha beta. So okay. At 4 derivative, what are the terms you can write down? At 4 derivative, you can write R mu nu, you can write R squared. So let's put the coefficient here. B plus C R mu nu alpha B beta squared. Right? There are 3 coefficients.
There is a name for this, right? The generalization.
There are many names for this. There are 3 ways of getting some structures out of this. There's the Gauss-Bonnet terms, there are the other terms. So all of these guys are related. They have analogs and gauge gravity dualities. But higher derivative means higher derivative. All right. This is I guess we've come to the end of QFD2. Are there any questions about quantum field theory? Ask all quantum field theory questions, I'll answer them all.
So, I mean, now sort of use the thing of coupling CM and inhibitor, so it's easier to think about. So, like, if I think of one over G as the coupling, Very colors, G. Okay, that also has a positive.
No, it's more, the analogy is more accurate if you think of this as a gauge theory coupling. That's 1/g squared. That's more the better way of thinking about it. Because gravity is like a gauge theory. Like the simple setup, I can make this very well. The gauge group is the local Poincare. Say Lorentz, local Lorentz. So that's a non-compact gauge group. We mentioned non-compact gauge group. It's all usually they lead to pathologies, blah blah blah. Sorry, did I address your question? I didn't.
So you're saying that this is.
Yeah, that's a gauge theory, correct.
Their G was, the difference is that their G was not marginal. Classic.
Oh, yeah, correct.
Yeah, actually, a very good question I'm gonna ask you anyways. So if we, what do you call it, gauge the Lorentz symmetry. So the relevant gauge field that pops up is the crystal, other crystals.